Right now, about 100 trillion neutrinos are passing through your body every second. They come from the sun, from exploding stars, from the Big Bang itself, and almost none of them will ever touch a single atom of you. To a neutrino, you are not there. The entire Earth is barely there. That is the problem. The neutrino is the ghost of particle physics. It has almost no mass, no electric charge, and it ignores the forces that let us catch everything else. Send a neutrino through a wall of solid lead a light year thick, and it has only a coin flip chance at hitting anything. So how do you build a telescope for a particle that refuses to be seen? You cheat with sheer volume. The odds of catching any one neutrino are tiny, but if you watch enough atoms at once, a few collisions become inevitable. The trick is finding a target that is enormous, perfectly clear, and free. Physicists found one at the bottom of the world. At the South Pole sits the IceCube Neutrino Observatory. Its detector is not a dish or a lens. It is a full cubic kilometer of Antarctic glacier, roughly 1 billion tons of ice that has been compressed over 100,000 years into some of the clearest solid material on Earth. To turn that ice into an eye, crews melted long vertical shafts with a jet of hot water, then lowered strings of basketball-sized light sensors deep into the glacier before it refroze around them. 5,000 sensors on 86 cables, frozen in place up to 2.5 kilometers down. But wait, if neutrinos are invisible, what do the sensors actually see? They never see the neutrino itself. They wait for the incredibly rare moment one slams into an atomic nucleus inside the ice and shatters it. That crash throws out a new charged particle, moving almost at the speed of light. Here is the beautiful part. Nothing can outrun light in a vacuum, but light slows down inside ice. So that new particle is briefly moving faster than light does through the glacier. When a charged particle breaks the local light barrier, it drags a shockwave of light behind it, a faint blue cone called Cherenkov radiation. The optical boom of a particle going too fast. That blue flash sweeps through the ice, and the sensors light up one after another. By timing which sensor caught the glow first and which caught it last, down to the nanosecond, the computers reconstruct the exact line the particle traveled. And that line points straight back to where the neutrino came from, out in the sky. This is why the whole thing points down, not up. IceCube's best view is of the northern sky, seen through the entire planet. The Earth becomes a filter that blocks everything except neutrinos, because they are the only things that can cross it. The one particle we struggle to catch is also the only messenger that can travel straight to us through a star or a black hole without being absorbed or bent on the way. In 2017, IceCube caught a single high-energy neutrino and traced it back to a blazar, a supermassive black hole 4 billion light-years away, firing a jet of matter almost straight at us. For the first time, we had located a violent object in the universe using a particle instead of light. That is the payoff. Telescopes see the light a catastrophe gives off. A neutrino comes from inside the catastrophe itself, and we catch it with a block of frozen water at the bottom of the world.